Everyone. It dawned on me we're very close to being halfway through. Doesn't time fly when you're having fun? So not only halfway through today, but halfway through the conference as a whole. I wanted to very quickly introduce our next speaker. All the way, I should add, from Moldova, which, for those of you not familiar with European geography, is somewhere that even the Europeans probably couldn't put on a map. So traveled a very long way to join us and to talk about DustMite, amongst other things, all in the aid of getting rid of bugs in D. So without further ado, Vlad, take it away.
Thank you. So today's topic is going to cover DustMite as well as a few other tools which I've written over the past few years. Hopefully they will help you with, well, the title of this talk is intentionally ambiguous. So it's going to cover both reducing bugs in D itself and in D programs. DustMite will be the main focus, and I'll also cover also a few other tools which will hopefully help you avoid other unpleasant situations. So a question to the audience. Have you ever finished writing your awesome D project, and when you try to compile, you got this? The error message in somewhere on Phobos, what's causing the error message in your code, only the compiler knows. Or this. No file or line number, nothing, just an error message. Or this. Or this. Or this. Or this. Or this. Or, well, you get the point. Okay, this is a joke, but all the other ones are real. They're from Bugzilla. You can find the issue number in the corner. So this is, of course, well, hopefully the answer to the question is no, especially for lately, because the quality of the implementation has been improving dramatically. But nevertheless, this has been a problem during this development and growth, and has been an issue both for D users, but also for D developers. Because when a user encounters a problem, they're not going to sit hours and try to find the exact cause in the compiler, what's causing it. So as a result, we get bug reports like this. I'm just kidding. Our Bugzilla doesn't support attachments that big. But hopefully we'll never need to. So let's see. There is actually a scientific method for debugging complicated problems. It was formulated by Andreas Zeller. And it basically involves a binary search. You make a hypothesis, conduct an experiment which tests whether the hypothesis is true or false, and make a conclusion based on that. If the hypothesis is false, you try another one. Otherwise, you have a better understanding of the problem, and you can move on by refining the hypothesis. So for example, if you have a program with two components, A and B, and A generates data and B consumes data, and the program is crashing, or otherwise malfunctioning, the first step would be likely to examine A's output and see if it conforms to the expected output. So then you know whether the bug is in component A or component B. Delta debugging is basically an algorithm to automate that. And it works by taking the set of possible problems, creating a hypothesis where the problem exists in a subset of this, and continuing this process until it narrows down the problem to a very small set. So in the context of compiler bugs, you start off with the program that's crashing, and then you try to remove pieces of that program until you have the smallest possible program that exhibits that compiler, that shows what the compiler bug is. Tigris Delta is an implementation of this algorithm. It is a Perl implementation of the Delta debugging algorithm as described by Mr. Zeller. It is mainly for C and C-like languages, so it has it recognizes the curly braces syntax and tries to construct a tree, and using that tree, it tries to remove parts of the program and see if the bug still manifests. But however, even though some people have tried using it in decode, it has some limitations. So it does not support multiple files. You have to figure out a way to put everything to one file or run it multiple times. It doesn't support Windows. It basically assumes a POSIX-like syntax. And, well, it's outdated, and of course, it's written in Perl, so good luck trying to fix anything in it. About 3 years ago, Dan made a post on the DNews group with a proposal for someone to pick up a very simple task. So what he needed was just something to remove all comments and unit tests from a program. So I thought I'd make a step further and wrote a tool which I call DustMite. DustMite is like Tigris Delta, but for D, but it also has a bunch of additional features which make it much easier to use. Native Windows support, of course, because D makes it much easier to write cross-platform code. The output is more readable than you would get with Tigris Delta, because Tigris will not preserve indentation. So it will just take the white space between two tokens, and as a result, you will get a misindented mess, which is kind of difficult to comment on. DustMite tries to make the output readable intentionally. Of course, it's written in D. It recognizes some D-specific syntax, which makes its output more tractable. And of course, it's not written in Perl, which is a plus in itself, in my opinion. Using DustMite is simple. You just need to give it a directory containing the source files and a test command. So generally, the source directory should be a copy of your program source code minus any temporary files or any files which are not needed to build your program and reproduce the bug you're trying to reduce, of course. And the test command is a command which will be executed and should return a status of 0 if the bug still manifests in a modified copy of your source directory, and 1 if the bug is no longer there, or there is some other problem, like DustMite created an invalid syntax file. So here is an example. This is for a simple example. We will start with a typical hello world program and try to get the simplest, smallest program which still compiles. So we run DustMite by specifying the source directory, the test command, which will be just in compiler invocation. The compiler satisfies the requirement of the test command because it will return a non-zero status when the source file given to it is invalid, and a 0 status if compilation and linking succeeds. So DustMite, upon execution, will print a bunch of stuff, a nice progress indicator, and at the end, it will give you a report. So here's, for example, done in 27 tests in 1 second, and the important bit, the reduced version is in src.reduced. It appends a .reduced suffix to the input directory. So what's in there? Well, the smallest D program that still compiles and links. So what exactly is happening here? Let's look at a step-by-step analysis. The first thing DustMite does after loading the input is it runs the test command to check if it is correct. So the test command on the input should return 0. Otherwise, if it returns non-zero, then DustMite doesn't have a starting point from which to start reduction. If a bad test command is specified, DustMite will simply try in vain every possible reduction looking for a 0 status and will not find one. So this is like a sanity test to see if the input corresponds with the test command. The next thing DustMite does is incidentally trying to remove the entire program file. This is also, even though this is not a hard-coded in the program logic, this is the first step in reducing the tree, which holds all the code. But this also serves as a sanity test to check if the user-supplied test command will at least sometimes return 1, well, non-zero status. If it always returns non-zero status, DustMite will stop here and say, well, I tried deleting everything, and your test command still succeeds. So there you go, an empty directory. The second test it does is it keeps the file but deletes everything in it, because in a graph, that's in the tree, that's the next level. Of course, this will not compile and link unless you're using Windows, 32-bit. If you use Windows, an empty D file will successfully compile and link, even though it has no starting point, because our wonderful Windows linker, uplink, the 8th of its name, does not concern itself with such trivialities as the requirement for an empty point. So it will happily succeed and create a broken executable file that cannot execute ironically. So if you want to repeat this test, you can either use a +6 operating system or use 64-bit. Just add -M64 to the compiler command line. Then it will use the Microsoft linker, which doesn't have this feature. The next thing DustMite tries to remove is just the main function. So you're probably wondering, why does it go from bottom to top? And the reason for that is that generally the style in which programs are written so that declarations declarations are before their usage, like you had to write in C. So it tries to remove usage first, because usage without declaration doesn't make sense, but declaration without usage does. This is the next top-level block is the import statement. This program will also fail to compile and link because write-to-len is not defined. So a few tests later, it will finally get to the write-to-len statement. And this is the first successful test, well, except for test 0, which is the sanity check. In all future tests, since DustMite notices that this program still compiles and links without the write-to-len statement, it considers it as the next starting point. And the write-to-len statement will no longer be present in all future tests. So the next step it does is tries to remove these parentheses, because why not? Well, actually, you're probably wondering, why does it try to do that? Because this is not valid D syntax. And the answer to that is that DustMite does not try to be smart or clever. It tries to be thorough. This has several advantages. The most important of which is that, well, if you have, I could use a D-lexer to parse the D code, but the problem is that if this lexer is, the more bigger it is, the more likely this lexer is to have a bug. So you really don't want your debugging tools crashing on you. So that's why the DustMite parser is intentionally simple. But usually that's not a problem, because DustMite tries to save you your own time by allowing you to do something else in the background. Some reductions for very large projects and very slow compilation times can take a long time to run, like even days. But you can do other stuff meanwhile. So it's just, it takes the problem off your hands for a while. Finally, it gets back to the import statement. And after removing that, you get the empty D program, which is the smallest program that can compile and link, with the exception previously mentioned. Internally, DustMite's representation is rather simple. It just has a tree of, well, this is the tree. The head is a string. The tail is a string. Both of these are slices of the input program. And the children are just referencing the same class. This is not the actual representation, but this is the basic idea. So here is the write-to-len statement as it is seen by DustMite. Each node is individually removable, so DustMite can, for example, try to remove the hello world string, the world statement, or some combinations between. And if you run DustMite with the --dump option, you can get a preview of what it sees in a text file. So this is the same thing, but as you would see with --dump. Let's look at a practical example. Let's say you're trying to compile your awesome project and you get an internal compiler error. So the way you would want to tackle this is run DustMite, specify the source directory, and as the test command, specify the compiler command that you use to build your project, but pipe it through grep. Grep will search for the error message or a part of the error message that you specify, and will return a status of 0 if it is found in the output, or 1 if it is not found. This is, as once again, very fits nicely into DustMite's usage, because DustMite will then only try to remove parts of your code if after the removal it will still create the same compilation error. So using this example, you will get a oh, this is too early. You will get a simple test case that still manifests this problem. A very common occurrence, well, not so much lately, thankfully, is when something works in one diversion but doesn't in the other. In this case, you will want to, so if you try to compile your program with 20642, for example, and it works, in the next version it doesn't. So how do you try to find the cause of that? Well, this is your clue. You'll want to create a script file which will return 0 if the program given to it will compile in one version but not the next. So this is an example for Bash and one for Windows batch files. The basic idea is the same. You just negate the result of the second compilation, so that and with the set-e switch, the bash script will succeed only if the first compilation succeeds, the second doesn't. The same idea for the Windows, but it's more explicit. The same basic idea also applies to problematic switch, for example. If you try to pass inline and your program crashes, you use the same idea. Create a script file which compiles with and without inline, and you will get the smallest program which exhibits this bug. DustMite will not always create the smallest test case from the first try. There are some things it cannot reduce. For example, if there is an unused function parameter which has a complex type, it needs to be removed both from the call side and the caller side. So since DustMite represents everything as a tree, it doesn't know the correlation, and it would be very difficult to implement that without also implementing a large part of the syntax. So if DustMite still creates a result with a very large reduced directory, you can try to simply edit the output and run DustMite on the new directory, and it will continue with your assistance. Sometimes sometimes compiler bugs, after reducing still rely on the standard library. When filing a compiler bug, it's generally beneficial to create a standalone test case. You just not rely on it. So the way you can do that, there are several ways, but the way I use at least is to just copy the source code of Phobos into your project and rename the std directory which you just copied to, like, for example, mystd, and then replace all occurrences of std to mystd. So this invocation here will do it for you. And that's all you have to do. The reason you have to do that is twofold. One is you want DustMite to actually reduce the source code of the std directory. Even though it's imported, most build tools, for example, RDMD, will ignore imports in the std package. They will omit them from the compiler command line because they expect them to be in the phobos.lib file. And the second is that you also don't want to link against the version in the phobos.lib file. So there you go. Oops, wrong button. Another problem, which is something I would call a false reduction, is when DustMite sometimes makes a misstep. So in this example, we have a buggy function which accidentally modifies a global, the I variable. So the loop is missing a variable declaration. If you try to reduce this program simply by asking DustMite to give you the smallest program that still trips that assert over there, you will get this program, which is very likely not what you were looking for. This removes the buggy function, this removes the variable assignment, and this result is useless. So there is no silver bullet for false reductions, but one thing you could do is, oh, timer didn't start. One thing you could do is add an assert which is annotated with a special comment. So this comment will later instruct DustMite to not remove any line. So this is a regular expression here. To not remove any line which contains this magic keyword. DustMite is not going to touch that line, and that line will remain in the reduced program throughout every step of the reduction. It's going to force DustMite it's going to force the program to validate that I is still 2 at that point. It will only try to reduce anything that modifies I past that point. So in this example, it will just give the entry because this is an example on paper on something practical. It will hopefully get you a more useful result. Another example of false reductions is with segfalse. So here we have a function which is destroying the contents of the class called C. And if you try to call the function later, it will crash because it will functions in D, methods in D are virtual by default. So it will try to access the virtual function table, which will point to null because destroy knows the virtual function table, and you will get a segmentation fault. If you try to reduce this program with DustMite and tell it to give me the smallest program starting from here that still creates, say, a seg fault, you will get this program, which is obviously not what you wanted. It's just calling a function on an initialized class. There are many ways to approach this program. One, if you have a test case if you have 2 test cases and the program succeeds on one and fails on another, this is your best bet because you can use the same approach as with several compiler versions or the several compiler flags to run 2 instances of the program and force one to succeed and another to fail. And this will give you the smallest program that still exhibits that difference. Another possibility is to examine the crash details. So, for example, you could run the program under GDB and tell it to print a stack trace, and then examine that stack trace to see if the program is crashing in the place that you need, whether in the function or there is a function that you need in the call stack. You can use marked asserts, as I have shown you in the previous slides, to force certain values to force certain tests to succeed at certain points in execution. Or, of course, if everything else fails, you could just throw DustMite out the window and use reduce by hand. So a while ago, Dan asked me if I could also implement a coverage support. For example, you have a program which has a bug that is very difficult to reproduce. It may require user input or network activity, and there is just no way to run it through DustMite automatically because you can't supply the same input every time through its hundreds and hundreds of attempts to reduce the program. But DustMite can still help you here. The decompiler has a -conf switch, which will, programs compiled with that switch, when run on exit, will create a listing file which looks like this. They show every line in the program that has executable code, and will also show the execution counts of each line. So with the -conf switch, you can tell DustMite to create the smallest program that still compiles and links without touching the lines that actually executed. This may help you to seriously narrow down the search space of the bug. And you don't need to run the program each time, just compile it. So this will allow DustMite to work independently and still create a useful result. Oh, this is an example of relocation. All you have to do is create a conf directory because DustMite needs the -- coverage switch of DustMite takes a parameter which indicates from where to load the listing files. And after you run your program, simply move your listing files, which are generated by your program, or more specifically the D runtime, into the conf directory and run DustMite. And this is what you'll get as a result. So you'll notice that the if branch that never executed got removed, and this switch which did execute was left in place. And the global variable, which was unused, was also removed. There are a few more helpers, which the last two you can find on the DustMite wiki. Timeout is a standard utility included with most POSIX systems. You can also get it on Windows when you use Cygwin or some other flavor like MSys. It will restrict the execution time of your program so that DustMite can keep running even if the compiler or your program enters an infinite loop. This can happen, for example, when it tries to remove the last element on the for loop syntax. The no crash dialog, well, the last two are Windows specific. No crash dialog will suppress the standard program has stopped working dialog, which will pop up whenever a program runs into an unhandled exception. So most Windows, the D runtime handles most exceptions, including most Windows native exceptions. But it will not handle stack overflows, for example. So in order to handle stack overflow, it needs more stack, which it can do. So it will simply crash and show this dialog. And no uplink MBOD will suppress the standard uplink, unexpectedly uplink termination error, which Raynor has done a great job and other contributors of patching up uplinks, so hopefully you will not get these very often anymore. But still, if you need it, it's there. The way you use helpers is you simply insert the command before you run the compiler invocation, which will run or compile and run your program. So for example, if a normal DustMite invocation has the command rdmd awesome, just insert timeout with this desired parameter in front of it, and it will continue running even if the compilation or execution will take longer than 5 seconds. Reduction is not the only thing that DustMite can do. Let's say you're working for a huge company and you're working on a super secret project, but you encounter a compiler bug. And the test case is still too big to reduce manually any further. For example, you can't reduce it any further because it's a very, very complicated bug. But you still can't submit the reduced output as is to Bugzilla because it might contain some confidential information. So DustMite helps you here as well. For example, if you have a project with 2 files, and run dustmite --obfuscate with the source directory of the program and specify the build command for your program. It will try to in turn rename every single identifier in your program to a successful name, and you will get a result with something like this. So notice that all the user identifiers have been renamed to single letter identifiers, and also the file name has been renamed as well. So the import statements, the model statement, and the file name have been renamed to something else. And this program should still compile, link, and do exactly what it did before that. A few people have integrated DustMite into their projects. For example, Alexander Bothy is the author of the excellent MonoD plugin, which is for Xamarin Studio and MonoDevelop. And he has added DustMite integration into the IDE plugin. So all you have to do is right-click on the project in the project tree and select Invoke DustMite. And this dialog will pop up where you can customize the parameters and execute the reduction. MonoD will take care of the dependencies of your project. So if you have multiple parameters specified in the IDE, in the project settings, it will take care of that for you and fill in the build command. So you don't have to mess with executing the IDE to build your dproj solution throughout every invocation. Another integration of DustMite has been done by Zunke, the author of the dub utility. And now if you run dub dustmite --help, you'll get a little wall of text which gives you the help information of how to reduce dub projects. So this is very useful because dub projects can have dependencies, and the dependencies can be all over the file system. Normally, you would have to get all these dependencies together into one source directory, and then you have to create a build command by hand. But dub does all that for you. And you don't have to mess with grep or checking error levels either, because you can just specify them using the dubs parameters. You can, for example, tell it, give me the smallest dub project starting from this one, which still gives the following linker error, specified as a regular expression. Or you can tell it, give me the smallest project that fails to link, etc. So that's all for DustMite. You can find more information on the DustMite wiki, which is user editable. A few people have contributed some great scripts to help reductions in certain situations. And as a bonus link, sscce.org is a website which promotes simple, self-contained examples. So whenever someone posts a huge zip file on the Bugzilla, you can point them to this site and tell them what's wrong with their Bugzilla submission. So I guess that's it for part 1. Let's go back to a previous slide. Here. DustMite can help you find the smallest program that still fails, that succeeds to compile in one example, but in one compiler, but fails to compile in the other compiler version. But that still doesn't answer the question, why did that happen? It worked in one version, and now it doesn't work, so something must have changed. What changed? Luckily, we do development in Git, which has this awesome command called git bisect. And git bisect can do a binary search between 2 Git revisions and find the exact revision, the exact change, when the condition, the test you're looking for, has changed its output. There's one problem with git bisect. This is the git bisect man page. But this is not the only problem. So git bisect is great at doing binary search between any 2 points in a repository. So for example, it can go, if you tell it that that commit over there works, but that commit over here doesn't work, or vice versa, actually, because we're doing regressions. It will go on and help you find the exact commit where it happened. However, D doesn't store its source code in one repository. We have 4, at least. And you can't do binary search across 4 repositories. And even if you wanted to somehow get them together in one single tree, there's no obvious way to do that, because Git commits can have multiple parents and multiple children, so it's a direct DAG, directed acyclic graph. And there's no obvious way to merge those. However, it turns out that there is a simple solution. Generally, when people clone D from the Git repository, they don't get something like, for example, over here. They will never see this commit, because this commit is part of a pull request. And whenever someone clones D from GitHub, they will actually get something that ends at a certain pull request merge. Well, hopefully, lastly, we've been doing that, as a rule. Sometimes people still push to the repository directly, but hopefully that will no longer happen. So everything is done via pull requests. Everything is nice and tidy. And we can just look at the state of the master branch on GitHub as the history of D. So we ignore everything else. And this is really trivial to merge together. So I have a program that does exactly that, and you get a history of the development that looks like this. Nice and linear and trivial to do binary search on. So I was actually going to talk about how to use git bisect, and it's specifically git bisect run, but that would have made my talk a lot longer, because there are some pitfalls you have to be aware of. And for example, if you swap if you accidentally specify the test command to be the git bisect run incorrectly, it will give you an invalid result, but it will not give you any clue that that happened. So I went and wrote a program to do it for you instead. The program is called Digger, and this is the simple invocation for finding the cause of a regression. You simply specify an ini file, which is also really simple. You have to specify the good revision, when something still worked, the bad revision, when it doesn't work, and the tester, which is very similar to what DustMite accepts, a command which returns 0 if the bug is still present, and, oops, sorry, backwards, if the program still compiles, so the bug is not present, or 1 if the program is already crashing. So this is past the point where the regression was introduced. And you can specify the good and bad commits in a number of ways. You can give it a SHA of the pull request merge. You can give it a date, though you have to prepend it with the ampersand sign. Or you can give it a ref name. For example, you can give it a version name, v2065, and it will look up the git tag for every component in the D organization, or any combination of the above. So you can say, for example, master at 1 month ago, or the release branch 2064 at a specific date. It doesn't have to be a relative date. So after you run it, after a while, it will give you a result like this. It will print the exact commit, detailing the merge. It will also include a link to the pull request. So if you want, you can click on that and tell the author and committers how much you appreciate their contribution to the deprogramming language. So I thought, well, I wrote a program that can build any version of D. So I decided to expose that functionality to a separate command. So we run digger build, and it's going to go and fetch the D source code from GitHub, and also get the dependencies on Windows like DMC and uplink, and unpack them to its own directory. And it's going to go and build everything from source and give you a nice directory with the compiled version of D. That includes the compiler, the runtime, the standard library, and RDMD. So then I thought, why not also allow users to build any D version? For example, give me the build from 3 weeks ago, or any specific tag, or previous versions of D. This is the third example is using a branch. Oops, sorry, the third example is using a tag. So this should be the tag when the zip file was created, hopefully. It depends on the release management. You can also ask it to make 64-bit builds if you like. And any combination of the above. So I also thought, why not also allow it to merge pull requests that are still open? So I added that. You can say master plus DMD hash 123, and that'll add the pull request that's on GitHub as it is right now, and merge it into the whatever master is right now, and try to build that. So then I thought, why limit yourself to pull requests? So you can specify also arbitrary branches and forks. So master plus username. Username is the GitHub username of whoever has DMD forked, and awesome is the branch name of wherever they have some exciting D features. So then I thought, well, the command line is nice, but not everyone is comfortable with it. So why not add a web interface? Included with Digger is a program which you can run, and it will give you some, it will start up a browser window and open up a web interface where you can set different options. You can select which pull request you'd like. You can set which version of D you'd like to build, not pictured here. And also, you can browse through all the forks on GitHub of every single person who forked D or a D component and add their fork as well. So I think this is really great because this allows people to experiment more with potential D features. So for example, if someone comes and say, I'm really missing this feature in the language or compiler, maybe someone says, I would like a bug fix for this bug, and someone else comes along and says, well, I have some work in this branch, but well, you'd have to build from source code because I'm not the DMD license does not allow me to give you a zip file. And the first person says, I have to build from source, I have to get Git, I have to get DMC, I have to get all this set up, I have to copy them over there, and they just forget it. So I think this will open up, I hope that this will open up more testing within the D community of potential improvements in the language, as well as the standard library. So what else can we do with it? Well, since we can build any D version, we can also make some, collect some data about all previous D versions. So this is, for example, the history trend of the size of the executable file of an empty program, just void main. Open brackets, close brackets, open squigglies, close squigglies. So there's nothing too surprising here. And this line here, I don't have data here yet. My build is failing because, well, technically there was the time when we had a broken version of our DMD in Git because back then no one was using it. So I'll probably have to add a workaround for that. I just made this chart this morning. So this is not very surprising. The runtime has grown a little. But what I found something more interesting is the size of the hello world program, which simply imports std.sdo and prints hello world. I have no idea what's going on here. I collected the data just this morning, and I still yet to look up what's going on. But the good news is that we are better than when we are started. So there's that. So that's it with Digger. Git is the project that generates the Git repository. The second link is where the D repository actually is. It is on Bitbucket because, well, I tried to do it in GitHub, and it notified every single author of every single pull request, and it was a mess, so I pulled it out of there. And the third is the actual program that I've described, which will allow you to build any D version, plus pull requests, plus forks. And I'd just like to ask you that Digger is kind of in a state of flux. I'm still working on it. If you encounter a bug, please let me know. This is what the logic looks like. So there's still lots of stuff moving around. So please try it, and please let me know if something needs improvement, because it's still a work in progress, and I really appreciate your feedback. So let's talk about another problem. This is not technically a bug, but it's still an unpleasant situation. Let's say you compile your awesome program, and when you look at the output, you get 12 megabytes executable file. Why? I mean, your program might not even be that big, but something is causing it to make this huge executable file. So generally, the answer to such problems has been, well, look in the map file. Great. Look in the map file. Does this make a lot of sense to you? Map files are a really technical compiler output, which is kind of hard to make sense out of. But I think we can do better, especially since D has a model system, and everything is arranged hierarchically, so we can visualize the data just in that way. So I have a project which takes a map file and gives you a tree map visualization. Every box here is a component in the model hierarchy, with some exceptions. For example, this is the garbage collector, up to here. And up there, you can see std datetime, second place in the module list by size. This should allow you to give you, well, if something is taking up a lot of size, this should give you a clue what exactly it is. But there still remains the question, why? For example, you may find that this tool will show you a component which you never intended to use, so why is it in your binary? The other tool I've written allows uploading an unstripped binary. So, sorry, Linux only for now, or anything that can be ELF format. It only accepts ELF format for now. But it's going to take your unstripped binary, run it through a disassembler, and give you a listing of every symbol and everything that it references and is referenced by it. This is still like rather minimalistic. Hopefully someday we'll get more coverage, because currently it only looks at function disassemblies, so it won't look at virtual tables. But it will still hopefully give you a clue of what's going on. Some of the common culprits are, though, statically linked libraries. So if you link in SQLite, that's going to take a big chunk of your executable file. That init, a special word about it. If you, for example, have a structure with an array of 10,000 integers, and also another field with an integer which is initialized to non-zero value, all of that is going to go into your program as a single blob. So you'll want to keep zero initialized structures separately, because then that will be optimized and will not be stored as is. Oops, it wasn't done here. Another thing is template bloat. Well, I think you're familiar with that one. the common solution is just to move as much code away from templates and into non-templated functions so that you don't repeat a lot of code inside your template function so it's not repeated. And a special word about classes. Since in D, all functions are virtual by default, every single method is going to be in the function virtual table, even if you never call it. But also, since we have object.factory, every single class is also going to be linked in your program, even if you use it or not. So I think this is not a very ideal situation, but it's something you need to watch out for. If you really don't need a class to appear in your program, then you need to add a version statement before it to exclude it from being compiled and linked in. So that's it with these two. You can find an online instance of these programs on the first link, where you can upload a map file or an unstripped binary. And the source code is at the second link. Oops. Another problem that's commonly occurring, well, hopefully not very commonly, is long build times. So people have been complaining in the past that, well, at a certain point, their project grows really large, and D is starting, even though it compiles very quickly, it's starting to bog down, and development slows down. So I've also written a tool which will, given a D program, it will attempt to give you a nice result of what's actually taking so long to compile. Here is an example. In this example, for example, the blue parts represents the time spent parsing the imports. Generally, you don't need to look at that because the total build time will be a sum of the red and green parts. So here we can see that, for example, std_uni is taking a long time to parse and also a while to compile. Everything else, except for some std_path, for example, is taking rather a small amount of time. The blue part is the time spent parsing just the imports from that model. But since generally they will be parsed only once, you don't need to pay attention to that. It's invoked by this command. First run dbuildstat that will create a .buildstat file, and then pass the resulting buildstat file through make_svg, which will create a chart as the following. This tool was actually created for a practical purpose to see why vibe.d was taking that long to compile, and with great success, we have found that vibe.db.mongo.connection was taking a really long time to parse. And the reason for that was that it was using regular expressions. So after rewriting the code to not use regular expressions, the compilation time has been improved.
Question.
Yes?
So that nice graphic you have looks a lot like waterfall, more like Niagara because everything is in kind of parallel. And the obvious question would be, is it possible to parse all of those modules in parallel? Is there an impediment to it?
Well, that's a question for the compiler writers.
I guess I'll get one on the line. Fortunately, we have one handy right here.
Well, the easy answer is if you put all the source files on the same command line, it only parses each import once.
That's correct.
If you have if you do multiple builds or incremental, I guess separate compilation.
Right, right.
The compiler doesn't know anything about what other runs of the compiler are doing, so it starts all over again.
Right. You only need to look at the blue parts if you're doing incremental compilation. Otherwise, they will only be parsed once. The blue parts are the sum of the red and green parts for the imports of that module. And the total compilation time for non-incremental builds will be the sum of the green and red parts, not counting the blue parts.
One other thing we've talked about doing is, although you can't get away with not parsing the imports, you can get away with not doing the semantic analysis of them. In other words, making the semantic analysis of imports fully lazy.
Yeah, that would be great.
I'd like to get to, and that will substantially speed things up.
I guess the conclusion is we're going to put a lieutenant on it.
Oops. Oh, one more thing you can do with the data that's created by the dbuildstat program is get a graph of all the imports that might be useful for some projects. Here's, for example, the import graph of a very simple program that just imports most of Phobos. And if you're thinking there's something wrong with this graph, you'd be right because it is incomplete. It is actually optimizable to remove, for example, if A points to B and B points to C and also A points to C, it's going to show only the A points to B and B points to C. Otherwise, it will be a completely unreadable mess. So I think we've talked about how many models in Phobos import many other parts of Phobos, and this is an illustration of that. So that's it with the tools that I wanted to discuss. This is the link to the dbuild tool, which will give you a diagnosis of why your program's taking so long to build. And I'd just like to give you a sneak preview / postmortem of a tool I created in 2009. It's called Diamond. This is a D-memory debugger and offline profiler. Its current state is that it is D1 only and does not support multiple threads, but it's something I'd like to work on updating and including, getting up to speed to the current D and garbage collection work. So it works by having a module and a postmortem log analyzer which reads the model's output, and what it does is the model integrates itself between the program and the garbage collector, or creates a binary log file which is read by the analyzer and allows you to get various information like which stack trace allocated the most memory, or why, most importantly, why is this block of memory not being freed by the garbage collector. So there is a command you can run. It's not pictured here, but it will give you the exact chain of pointers and what allocated them to tell you why a block of memory is not being freed. This tool was indispensable for me while I was debugging a memory leak in some of my projects. I'm going to work on this project this year, hopefully. This is another example. It will give you the stack trace, so it will also read the map file of your program and give you demangled names. And that's it. I just like to talk about some future plans. Digger currently does not create something that you would find in a zip file. It only creates the minimal binaries required to build programs. So something I'd like to add is actually installing it somewhere so the user can use it immediately, because right now you have to add it to path. Packaging, so you can create a zip file similar to what you can download from dlang.org. Include extras such as the curl or SQLite library, so you can just use std.c.curl or std.net.curl or stdc.SQLite. For DustMite, one thing that's been often asked about and something I've also been thinking about is parallel reduction, so getting it working even faster. And for Diamond, of course, D2 support, threading support that will come with it. And the two will probably be achieved by creating a fork of the D runtime, which you can install by using Digger. So that's all for my talk. Thank you for listening. And any questions?
All right, we have time for questions.
It looks like Digger can actually help a lot with trying out new DMD beta releases. Have you considered adding some features for discovery and probably promoting of running beta release and promoting users to try it out?
Yes, absolutely. I think we talked about nightlies last year. I'm not sure where that plan went, but it doesn't matter because with Digger you can get the latest, the very, very latest master branch just by running one command or starting up the web interface and just clicking a few buttons. So absolutely, yes. I think this is a great direction to consider.
Any other questions? No? All right. So thank you again, and we'll be back here at 2:30, 5 minutes. Thanks very much.